Good evening and welcome to yet another episode of Kavi's Corner. And today we have a very special guest, an old colleague from Oxford University, Professor John Hughes. And he's going to talk about something very close to my heart called functional programming. The talk is entitled The Promise of Functional Programming, What It's Delivered and Where It's Going. So I had done my PhD in this area many years ago in the interface between functional programming and graphics. And when I came to Oxford University in 1983, John had just completed his DPhil, and he was on his way out maybe in a year's time, year or two's time, where he got at a very young age a full professorship at the University of Glasgow. So a little bit of background would help to both him and the topic today. So he's originally a mathematician from Cambridge, right? He did a very good BA in math, and then he did a diploma in computer science uh, with a distinction at Cambridge, and where he developed a compiler for a functional language, including something called a strictness analyzer. Now, it's quite interesting that a person with a math background should switch to computing and start writing compilers at that time. In fact, his DPhil, his PhD thesis at Oxford, was the design and implementation of programming languages, but he did a very good work on super combinators, which maybe he'll speak a little bit about. Okay, so basically functional programming enthusiast for many years, almost 3 decades at the universities of Oxford, Glasgow, where he went. And since 92, he's been in Chalmers University at Gothenburg in Sweden. And he's the co-designer of a very important functional programming language called Haskell and QuickCheck. And he's also served on the Haskell Design Committee, and he's the author of almost 100 papers, many of them classics. He's created a tool called QuickCheck, which I hope he'll speak about with Kern Klassen, the most popular testing tool amongst Haskell programmers. But I wonder why testing? Functional programs are meant to be correct by design. I hope he'll answer that question also. And in 2006, he founded Cubic to commercialize this technology using Erlang. Erlang is also a very interesting language which is used by Ericsson to build switches. So I hope he'll talk a little bit about that also. So he's done many things in this area. He's one of the main forces behind the entire functional programming community. He's been trying to put functional programming to work in software design and verification using domain-specific languages. He's got a project with that title also with this Swedish research council, and he's on the program committees of many important workshops like AST 2010 and TAIC 2010, which is a testing conference and so on. So someone here with vast experience and amazingly down to earth, and an old friend from the Oxford days. I'm delighted to introduce to you Professor John Hughes, who will speak about functional programming. John, over to you.
Well, thank you, Kavi. What a great introduction. Actually, I can add that I came across functional programming for the first time as a schoolboy programmer in 1975, I think it was, when I learned Lisp. But I didn't have a Lisp implementation, so I had to write my own Lisp interpreter in those days. It was awful. I found the code a few years later. It was so bad, but it enabled me to write Lisp programs, which is what I wanted to do. So I've been doing functional programming 45 years then.
All right.
Okay, I think I've managed to share my screen now. So let me see if I can get started. Okay, so Kavi asked me to talk about the promise of functional programming, what it's delivered, and where it's going. And that is an incredibly broad and wide-ranging title. So I'm going to give quite a broad and wide-ranging talk. I won't go into great detail about anything, but I hope that you get the gist from it anyway. So I want to start by talking about what is functional programming? What does it mean? And to do so, I'm going to show you the Hello World program of functional programming. So this is a program for computing the factorial function. N factorial is 1 times 2 times 3 times ... times n, the product of the first n numbers. And if you want to compute that with a computer, well, we know how to do it. You need 2 words of memory. You start by putting the value of n, maybe 6, in the first word, and then you put 1 in the second word. And now what we do repeatedly is we take those 2 numbers, we multiply them together, and we write the product back into the second word. And then we take the first number, subtract 1 from it, and write that back. And then we do it again. Right, so we're computing 5 times 6 and decrementing our counter to 4. And we do it again. And again. Getting close now. And again. There we are. That's 720. That's the answer. But we've still got to multiply by 1, of course. And once we reach the point where that first word contains 0, then we finish the computation. And the answer 720 is in the other word. So this is how computers compute things, right? You do your computation by reading and writing data in the memory. And that's the way that the von Neumann architecture works. So, of course, we usually program at a somewhat higher level than this, but the first programming languages and imperative programming languages are just a kind of thin layer on top of this underlying model. What do I mean by that? Well, if we want to write a program to do this computation, then we just give names to the memory locations. And then we write a little program that essentially does what I showed you in my animation. And if you look at that C code, it corresponds very closely to the animation that I showed you. So the very first compiler for a real programming language was the Fortran compiler. It was written by a man called John Backus. John Backus led the Fortran compiler team at IBM. It was in the late 50s. Great achievement. And he won the Turing Award for that. That is computer science's Nobel Prize, you might say. But by the time he won the Turing Award, he'd got fed up with this style of programming. And his Turing Award lecture was called, "Can Programming Be Liberated from the von Neumann Style?" Now, this lecture was turned into a paper. If you Google it, you'll find the paper online. And if you haven't read this paper, you really should. It's a classic of modern computer science. So Backus was pushing for a functional style of programming. What does that mean? How would we write a factorial program in a functional language? Well, I'm not going to use Backus's notation. I'll use a modern functional language, Haskell, that I was involved in designing. And here's the Haskell code that does the same thing. You compute the product of the numbers from 1 to n. Okay, so what's going on here? That 1 ... n, that computes collection of numbers from 1 up to n, and the product function just multiplies them together. That's all there is to it. So if you compare these two pieces of code, the code on the left and the code on the right, you can see that in the code on the right, there's a whole lot of things that you don't have to think about. You don't have to think about where the numbers are stored. You know, who cares where they're stored? As long as they're computed, that's all that matters. You don't have to care about whether all the numbers are stored in the same location. In the code on the left, we know that they are. In the code on the right, we can't tell. Actually, this may surprise you. If you compile the program on the right with optimization turned on, it's likely to produce exactly the same code as the code on the left. In both cases, all those numbers will be in the same location in a register. But you can't tell that from the program itself. It's just a question of how good the compiler is. Here's another question that you don't have to think about. What is the value of n afterwards. It's the same as it was before, obviously. Why would it be any different? Yet, in the code on the left, the code has destroyed the value of n. So that variable doesn't contain the right value at the end of the program execution. So there are a lot of things that in the functional program you don't have to think about. Instead, you think about, what am I trying to achieve? I'm trying to multiply together the numbers from 1 to n. So that's what I say in the program. I make the numbers from 1 to n, and I multiply them together. You think at a higher level in terms of larger units, like this collection of all numbers. That's in the problem statement, and so it also appears in the program. Whereas in the code on the left, then you're working one step at a time. Backus called this word at a time programming, and he was very, very critical of it. You could also call it piecemeal programming. So what we have to do is think of all of the operations that we need to do. We have to schedule them, decide what order to do them in, keep track of how far we've got, and make sure that we get to the end of the job with all the work done. So that's piecemeal programming. And some people have called the style on the right wholemeal programming, like wholemeal bread. So you know it's good for you. Why? Because we work with whole values at once, the whole collection of integers from 1 to n. Okay, so this is one contrast between functional programming and comparative programming. It's wholemeal versus piecemeal. Now, I'm sure many of you are thinking, wait a minute, what is this guy talking about? Lots of programming languages let us work with data structures larger than one word. So, for example, any programming language worth its salt will let us represent a car, for example, by an object with 2 fields, the make and the color, and we can work with this object as a unit. But in imperative languages and in object-oriented languages like Java, you still have to remember that this car is a data structure in memory. So that the von Neumann model is still there under the hood. And how does it appear? Well, this is a blue car. Let's put it into a collection of blue cars. That's clearly harmless. It's also a Volkswagen. Let's put it into a collection of Volkswagens. But now we have the same data structure, the same piece of memory in 2 different collections. And now there's a risk that whoever has the collection of Volkswagens may follow this pointer. There we are. They follow this pointer and decide to respray the car. Maybe they'll turn it red. And now if they do that, suddenly we have a red car in the collection of blue cars. So the data has been changed under our feet. I think of this as rather like what happens if you're looking at Facebook and you see a cute picture of a dog. And of course, you might like that. There we are, that's fine. You like the cute dog. But now the person who posted that photo may be malicious. And what they might do now is edit their post and turn it into something else. And suddenly, you have liked a post about a MAGA hat that you would never normally like. This is a kind of bait and switch trick where the data has been changed under your feet. And that's what happens in imperative programs. It's bait and switch. So the problem here is that this data, this car, is shared in 2 places, but it's mutable. That means it can be modified. And if the Volkswagen collection owner mutates that to red, then that's going to interfere with the blue car collection owner. So sharing mutable data like this, it's error prone. It's the cause of a lot of bugs and has been for decades. But it's particularly harmful in parallel programs. So suppose that the blue cars are being manipulated on one core and the Volkswagens are being manipulated on another core. Now we can have 2 cores simultaneously trying to update this car object. And that is dangerous. That risks race conditions. And if you have ever had to debug parallel programs of this sort, you know how hard those are to deal with. So in parallel programs, shared mutable data is even more error-prone. But it's not just error-prone. It's also expensive. Because if you're going to manipulate this correctly, you need to claim locks all the time, and that is very expensive. But also ask yourself, which core's cache is this data going to reside in? Well, if it's being modified by both cores, there's no cache that it can live in all the time. It's going to be playing cache ping pong and jumping to and fro between different caches. And that is expensive. So in parallel programs, shared mutable data is error-prone and expensive. This is not a good combination. But in distributed programs, it's even worse. If the blue cars are being manipulated on one node in the cloud, and the Volkswagens are being manipulated on another node, then there's no way that they can share this car data. So shared mutable data is a bad thing. And in functional programs, we don't use it. What do we do instead? Well, if we have this blue car and we want a red car in a functional program, what we do is we don't update the existing car, we just create a copy of it that is the same in every respect, except that its color is red. And this is the way that functional programs operate. You never mutate data, you create a new copy that is different in the respect that you need. And now we might want perhaps to put this red car into the Volkswagen's collection. But no, in a functional program, we don't mutate, we don't change the collection of Volkswagens. We make a new collection of Volkswagens that contains the blue car and the new one. They're both Volkswagens after all. So you can see that there's a whole style of programming here. But once you commit to not mutating data, then you need to follow that commitment all the way up. So you need to have good libraries. You need to have collection libraries that work in this way, that give you a new collection that is like an old one, but with an extra element, instead of actually changing the same collection in memory. So you have to be consistent. You have to have libraries that support programming with immutable data. Immutable is data that you can't change. And that's why when Rich Hickey designed Clojure, which is a functional language that runs on the JVM, then he re-implemented, or he wrote a new collections library instead of reusing the Java ones, because the Java collections worked in a mutable way, and that wasn't appropriate for Clojure. But he made some great implementations. So you can have, if you do it right, you can have very efficient collections that work in this way, where you get a new collection back when you modify something. And you can actually pursue this idea all the way up. There is a very nice database called Datomic that is also Rich Hickey's work, and it's produced by a company called Cognitect, that makes the whole database immutable. So the database never changes. Of course, you can add entries to it, but when you do that, you get a new database that differs from the old one in that it contains an extra entry. Cognitect say about Datomic that it's indelible and chronological. By indelible, they mean it's immutable. So that really does mean there is no deletion from the database. So what if you want to delete something? Well, what you do is you add a retraction to the database. So you never take anything away, you only add things. But one of the things you can add is, I retract that record. And then you can come back at this database and you can ask what was in it at any particular point of time. And if you ask what was in it at this point of time, then you will see the record that you have later retracted. And if you ask what was in it at this point of time after the retraction, then you won't. But the data itself is immutable. So immutable data, it was originally something that we used in functional programming languages, But as parallel computing has become more and more important, and as distributed systems have become more and more important, then immutable data has become something that many, many people use. And there was a very nice paper in ACMQ just a few years ago called Immutability Changes Everything. You might like to go away and read that. This talks about the importance of immutability and the way of using it, with a focus on databases and distributed systems. So there are all kinds of reasons for using immutable data nowadays. So the arrival of parallelism, so that was 2005, 2006, when the first multi-core processors came. Since then, everybody must write parallel programs if you want performance. And the huge importance of parallelism and distributed systems has been a big driver towards immutable data and towards functional programming. I want to talk just a little bit about a functional language called Adlang that Kavi mentioned in the introduction. And this is a language that it's a functional language with a lot of support for concurrent programming. It was designed at Ericsson for telecoms applications. And since then, it's spread much more broadly. So in an Adlang system, the whole idea is that there are many processes running at the same time. That's what these circles are supposed to represent. And I've drawn 4, but a typical Adlang system may have thousands of processes running at the same time, or hundreds of thousands, very, very large numbers. And these processes share no memory at all. So there's no shared mutable data. Well, there's no shared data. Every process has its own heap, its own memory. So data structures in those processes, they are also immutable. Adlang is a functional language. You don't change data structures. And if another process needs access to that data, then the only thing you can do is copy it into that process's memory. You send a message. That's the only way that processes communicate. And it doesn't matter if those processes are running on the same machine or on a different node in your local area network or a different node in the cloud. It doesn't matter. You write the code exactly the same way. And that means that it is very, very easy to scale an Adlang program. You just run it on more cores, or you run it on more nodes in a cluster. And because the program is already built as thousands of processes working concurrently, then you get very scalable performance as a result. Perhaps the best known example of that is not telecoms, where Adlang started, but internet services. Internet servers very often must support very large numbers of concurrent requests, and Adlang is extremely good at that. And perhaps the best known service of that sort is WhatsApp. You probably didn't know that the server side code in WhatsApp is all functional code. It's all in Adlang. And by using Adlang, they were able to support 500 million users with only 30 engineers, more or less. That was a huge achievement. It was a huge achievement back when it was true in 2014. They were so successful that in 2014 they were bought. Facebook paid $22 billion for them. And since then, they've only grown further. Their code is still serving every WhatsApp request in Adlang, but now it's serving 1.5 billion users. So you can see that in the role of Adlang, when you send a message on WhatsApp, it's Adlang code on the server side that is sending that message for you. There's functional programming going on at the heart of services that we use every day. Let me talk a little bit now about Lambdas. What are they? Well, I showed you this little factorial program in Haskell, the product of the numbers from 1 to n. That's one way I could write it. Let me show you another way I could write it. Like this, fold R of asterisk 1 and 1 dot dot n. What is going on here? So that asterisk in brackets, that is the multiplication function. And what I'm doing is foldr is a function that combines the elements of a list, but you can give it the function to do that. So I'm using foldr to multiply the numbers in that list, and so I pass in the multiplication function as an argument. Now, once I write foldr and use that instead of product, then of course I could decide maybe I want to add up the numbers instead. And I can do that just by passing in the addition function instead of the multiplication function. This other argument is a starting value. So when you multiply things, you start from 1. When you add, you start from 0. That's fine. So now this code here, this adds up the numbers from 1 to n. What if I wanted to add up the squares of the numbers from 1 to n? Well, I can do that in a similar style, like this. What's going on here? Well, the 1 ... n, that is computing the collection of numbers from 1 to n. Map does the same thing with every element of the collection. So I need to give it a function to call for every element. And that's what this lambda thing is, this lambda expression. This is the function that, given an argument I, returns I squared. So lambda notation lets me define a function in line, as it were. And it's very, very convenient for using functions like map and foldr. So the result of the map is going to give me a collection containing all the squares of the numbers. And then the foldr will just add all of those up and I get the result that I want. These functions like map and foldr, these are called higher order functions. They're functions that take other functions as arguments and do things with them. And this is a very, very common design programming method in functional programs. And it's great. It lets you put the smarts of your computation into the higher order function, into map or foldr. These are the functions that know how to traverse a collection. And then you just customize them a little bit by passing in the small function to define what it is that you actually want to do: multiplication, addition, squaring. So higher order functions are heavily used in functional programming. And to make them really effective, you need this lambda notation. Lambda notation has really made a long march into programming languages. So lambdas date from the 1930s, when mathematician Alonzo Church invented them. And they made it into programming in 1960 in the programming language Lisp, which is the first functional programming language that you could actually run. And since then, they have been in virtually every functional programming language. They were in ML when it was created in the mid-70s. They were in Haskell, which was defined around 1990. They were in OCaml from the start. They were added to Adlang in the late 90s. They were in Scala from the start, and F#. But then all of these languages are languages that you would call functional programming languages. So they're languages targeting functional programming. But in 2008, something astonishing happened. Lambdas were added to C# and Visual Basic. Why were lambdas added to Visual Basic? Well, it's all thanks to a man called Eric Meyer, who designed something called LINQ, Language Integrated Queries. And what these were was higher order functions like map and fold that you could use to write database queries. But to make use of those, you needed lambda expressions. And LINQ was so nice that it was added to all of Microsoft's programming languages. And so they all got lambdas at that time to support nice database queries. Well, once Microsoft had added lambda expressions to their languages, it wasn't long before C++ got them in 2011, and Java in 2014. And just this year, Excel. Excel is actually the world's most used functional programming language, believe it or not. And in 2021, it's getting lambda expressions. So this is really an example of a functional programming idea that has conquered the world, let's say. Just to talk about higher order functions a little bit more, I showed you this example that computes the sum of the squares of the numbers from 1 to n. And I talked about foldr, which is what this function is called in Haskell. But it wasn't always called foldr. The same function was in Lisp. And in Lisp, it was called reduce. Look at this, map, reduce. That should ring a bell. MapReduce is a framework that Google developed for large-scale data processing on clusters of hundreds to thousands of machines. And the map and the reduce in Google MapReduce are not exactly the same as the functions in my example, but it's the same underlying principle. What does Google MapReduce do? Well, it consumes and generates immutable collections of data that are spread across the entire cluster in the data center. And just as in the little example I showed you, all of the smarts are in the higher order functions. They're in the map and the reduce. Those are the things that are written once and know how to distribute this huge computation across the cluster, know how to keep track of what's happening, schedule new tasks, detect faults when they occur, and recompute things that fail. It's very complex making a large distributed system, like thousands of machines in a data center, work on a task altogether. But all that smarts is in the map and reduce functions. And all you have to do is write the little functional fragments that process each element and combine them, which is exactly what the map and reduce examples here do. And when you write these little functions for processing one element or for combining elements, it's very important that they don't have side effects. They have to be pure functions, because you have no idea when or how many times they'll be called. I mean, it might be that each element actually gets processed several times. Maybe it's processed on one node first, then that node crashes before the result can be used. The MapReduce implementation will then reschedule the task somewhere else, so your function is called twice, maybe 3 times. So they must not have side effects. If they do, the results that you get will be meaningless. So this is really, MapReduce is really an example of functional programming on a large scale. And it's been hugely successful. Before MapReduce was introduced, the code for building Google's web search index was almost 4,000 lines of C++. Afterwards, it was only 700. It was more than 80% smaller code to implement web search indexing. And MapReduce was so nice to use that after it was introduced, in only 4 years, Google developers built 10,000 MapReduce applications in their code base. So it really took off like a house on fire. It's a very interesting story. If you'd like to read more about this, there was a paper in Communications of the ACM in 2008. And this paper is the one I would recommend because it came out after 4 years of experience. So they're able to look back a little bit on what happened once they had introduced MapReduce. And you can see here, by that time, they were running 100,000 MapReduce jobs a day, processing 20 petabytes of data. So it's really a huge computations. Let's think a little bit more about higher order functions. One way of thinking about functions like map and foldr is that you give them little program fragments as arguments, lambda expressions or functions, and they build bigger program fragments from them. So you can think of it as using functions to build up your program. And another way to think of that is that these functions are the constructions of a special purpose language, a domain-specific language. So I've shown you a domain-specific language with only 2 constructions, map and foldr. But you can actually define much more complex domain-specific languages just by building a larger API of higher order functions that you can combine in many different ways to build programs that solve a particular kind of problem. This kind of domain-specific language is a common design pattern in functional programming, and it works at a really large scale. What it lets you do is identify a kind of problem that you need to solve repeatedly and then provide a specialized API of higher order functions that gives you a specialized domain-specific language for solving those problems really easily. I thought I'd show you a couple of examples, or just tell you about a couple of examples. One of them is at Standard Chartered Bank. One of the things that banks need to do, because they trade in financial contracts, financial products, they need to model those products. New financial products are invented every day, and the quants at banks like Standard Chartered need to figure out how to value them. At Standard Chartered, they do that using a domain-specific language in Haskell. And the quants build models of each of the financial contracts that they want to trade, and then those are deployed and they're used to compute the values of these things. And Standard Chartered are a well-known bank who do this. They have millions of lines of code in a Haskell dialect that uses this domain-specific language idea. But very many banks do something similar, in fact. So that's one example of a functional domain-specific language that's seeing a heavy use. Another one is spam filtering at Facebook. So there is spam on Facebook. I didn't originally realize this, but there is. And the way that they deal with it is that somebody has to identify the spam when it's reported to them or whatever, and then write a spam filtering policy. And they have every post that anybody tries to make anywhere in the world, and will filter out spam of that sort. So somebody has to write these spam filtering policies. And nowadays that is done in Haskell using a domain-specific language called Haskell. And this processes more than 1 million requests a second. There are a lot of people posting on Facebook in the world. And when they brought in a functional programming solution with Haskell used to write these policies, they got a 20 to 30% performance improvement over the previous system. Plus, it became much, much easier to write those policies. I thought I'd show you just a little example of some Haskell code. Here's a little bit of Haskell code that figures out how many friends X and Y have in common. So if you look at it, it's quite readable. I hope it's Haskell. It says, well, first of all, let A be the friends of X, let B be the friends of Y, then intersect those sets A and B, compute how many there are and return it. Looks simple. It also looks inefficient. Why? Because finding the friends of a person is a database query. And that involves the database latency, which can be long. I mean, the database may not even be on the same node in this case. And in this code, we look up the friends of 2 people. Right? So this policy is going to suffer 2 database latencies. That may be too long before the Facebook post has to appear. What Haskell does is analyze the code and realize that these 2 queries are independent of each other. And so Haskell automatically dispatches them both at the same time. As a result, you suffer 1 database latency instead of 2, and your code goes twice as fast. So that's what Haskell does, and that is another very successful use of this domain-specific language idea. Let me change gear a little bit and talk about testing. Testing is something that's very dear to my heart. But I want, first of all, I want to remind you of your experiences in testing code. I'm sure everybody has suffered this. You write some test code, the tests pass. Great, that's fine. And then you add something to the code that should not make any difference whatsoever. And what do you know? Your test fails. Now, when this happens, it's because you've forgotten about some interaction between these pieces of code. And in imperative and OO programming languages, that is so easy to do. And you end up tearing your hair trying to figure out what on earth is the connection between these 2 pieces of code. But in functional programming languages, this cannot happen. When you have a function, a pure function with no side effects, then only its input determines its output. There is no interaction with anything else, ever. And that means that when you test a function like that, you can see everything happening. All you have to do is give it an input and inspect the output and see if it's right. Let me just do that in practice for you. I'm going to show you, I'm just going to do some testing of the set library that comes with Haskell. So I'm going to test it in the Haskell REPL, the read-eval print loop, where I can just type in a Haskell expression like this one, and then hit return and it gets evaluated. So here I'm going to make some sets. I need a set to work with. I can construct a set from a list. So I'm going to make a set containing 1, 2, and 3. Hit return. That's the set. It's displayed in the form from list 1, 2, 3. But that's just a set containing 1, 2, and 3. Okay, so now I might like to test maybe deleting an element from the set. And I can do that. I can just call the set.delete function. Let's delete 2 from it. What is this it? Well, in the Haskell read-eval print loop, the variable it always refers to the last thing that we evaluated. So it is going to be the set containing 1, 2, and 3. And so if I delete 2 from it, what's the result? Hit return. It's a set containing 1 and 3, of course. And now I could continue using the it variable. It now refers to this new set. So I could, for example, put 2 back, insert 2 back into it, and I could delete 2 from it again. So I can play with the functions here and watch what they do and see that they're behaving as I expect. But what I want you to notice here is that this last set I ended up with is the same as that one that I saw earlier in the sequence. That makes sense, right? Because what I did was I inserted 2, and then I deleted 2. So obviously, I should get back where I started. And that should be true not only for 2 and this particular set, but it should always be true, shouldn't it? It should always be true that if I insert n into a set S and then I delete it again, the set I end up with is the same as the one that I started off with. So, of course, you could write a collection of unit tests that check that in a variety of cases. But what we do in Haskell is something different. We define a function. This is a function prop delete insert that takes n and s as arguments and performs that test for any n and s. And we read this as saying that for all n and s, it should be true that when you insert n and then delete it, get back where you started. So this is our test code. And we write tests not by writing unit tests for one particular case, but by writing properties like this that should hold for all values of the arguments. And we call this property-based testing, when your test code consists of properties instead of examples. It's very powerful. Now, of course, in order to actually test this, I need a particular n and s. So I could sit in the REPL and I could just call this function with different arguments, and then it would run the test for each of those arguments. But there's something else I can do. I can take this property and I can call a property-based testing tool, in this case, QuickCheck. I just give it the property as an argument. Now look, QuickCheck is a higher order function. It's getting a function as an argument. And what QuickCheck does is it searches for a test case that will make the property fail. And in this case, it actually succeeds. The property is not always true. And then we get some output like this. So if we have a look at this, what we see are the values of the function arguments, n and s. So when n is 4 and s is the set O that only contains 4, then the property isn't true. Why? Well, what are we doing? We're inserting 4 into that set. And if I do that, I can just call that in the REPL to see what happens. I get a set that contains 4, of course, but because it's a set, it only contains 4 once. So now if I delete 4 from this set, I'll end up with the empty set, not the set I started off with. So that's the problem here, right? If I insert an element that is already in the set and I delete it, then I don't end up where I started off with. What I want you to notice here is that what QuickCheck shows me is a minimal example. You basically, and it doesn't matter what the value of n is, but you can't get a simpler example that demonstrates this problem. That is what property-based testing tools do. They show you the simplest example of a failure where everything about that test case is relevant. And that makes debugging very easy. Now, in this case, there is no bug in the sets library. It is working as intended. We won't fix it. The bug here is that the property was wrong. My test is wrong. And of course, I can correct that. Here's an example of a correct property. If I insert something into a set and then delete it, that is the same as just deleting it. And if I take this property that is now true and do the same thing, then QuickCheck will run 100 random tests by default and then tell me that they all passed. And now I have much more confidence than I could possibly have by writing a number of unit tests. Actually, I would usually run 10,000 tests at this point. Why not? It only takes seconds. And then I'd really be very confident that, that the property is actually true. So all of this property-based testing, it builds on what I've already told you about. It builds on higher order functions. As you can see, QuickCheck is a higher order function. And there is actually a little domain-specific language, which you haven't seen much of, but there is, trust me, for defining properties and defining test case generators. So it uses all of those design ideas that I've talked about to make a tool that makes testing very, very powerful and simple. You might wonder, I've shown it to you on a very tiny example. Does it scale? Oh, yes. We've applied it to millions of lines of code and found all kinds of astonishing bugs with this testing approach. Let me show you my very favorite bug. This is a bug that was a race condition in a database. And this race condition was causing the database to crash at a large online payments company in Sweden every week or two. And when it crashed, the database was corrupted and they had to restore it from backups every time. So it was really a pain in the neck. So what is this example? Well, this is what you have to do to crash the database. First of all, you open a table, then you close it, then you open it again. Weird, yeah? But you have to do that. And then you do three things in parallel: one lookup and two insertions. And if you run this code, usually everything works. Very, very occasionally, the database crashes. So, of course, I wasn't the first person to look for this bug. It was causing so much trouble at the company that the database developers spent 6 weeks there looking for this problem. And at the end of that time, it was very hard to find. They thought, it seems to happen when the database is about 1 gigabyte. What do you know? When I tested it with a QuickCheck, it took less than 1 day to find this example. And given the example, it took less than 1 day to fix the problem. And if you look at it, this really is the smallest example that can provoke that bug. Open, close, open. Do you really need to do that? Yes, you do. The first open creates the table. The second one opens an existing table. It's very slightly different. And that difference was essential to make the bug possible. But you can see why they hadn't found it with a handwritten test. Who would write this as a handwritten test? It's just infeasible. The only way to find this kind of bug is to use some kind of automated testing, automated searching. So that's what property-based testing does for you. So property-based testing was invented by me and Koen Klassen. We built the first version of QuickCheck for Haskell. I started a company called Qvik, which works with property-based testing tools and services. But the idea is so appealing that it has been copied many times. There's Scala check that other people have written for doing property-based testing in Scala. There's hypothesis if you want to do property-based testing in Python. There's test.check in Clojure. So these are 3 examples of tools that I know are quite good. But if you look at Wikipedia, there are many, many, many more. virtually every programming language has adopted some form of property-based testing. So I will claim this as another success for functional programming. It's an idea from functional programming that has spread to virtually every programming language in the world. If you want to learn more about property-based testing, let me recommend a paper I published last year called How to Specify It. If you just Google that and John Hughes, you'll find it. And this is a tutorial paper that gives you a nice introduction to how you come up with properties for property-based testing. Okay, let me come back to my original example of factorial numbers. I want to talk about types. So what are the types of things here? Well, 1.n, that constructs a list of integers. And in Haskell, we write that type as int in square brackets. So that's fairly straightforward, I think. What about the multiplication, though? Well, that's a function. Its type is a function type. It takes 2 integer arguments and returns an integer result. And the way that we write that in Haskell is we put the argument types with an arrow after each one, and then the result type comes at the end. So, okay, that's the type of multiply, but what is the type of foldar then? Well, we can just look at the types of the arguments. It's got to be int to int to int, that's the type of multiplication. To int, that's the type of 0. To a list of int, that's the type of that. To an integer, that's the type of the total result. So this is the type of foldar. But if you ask Haskell what the type of foldar is, it won't tell you this. It'll tell you this instead. What are these A's and B's? These are type variables. So if you think about it, foldar wouldn't be very useful if the only things you could combine were integers. But by putting type variables there, you're allowed to use foldar with any type of this shape. The only thing you have to do is replace the variables by the type of the actual data. And you have to replace all the occurrences of A by the same type, of course, and all the occurrences of B by the same type. So if you want to combine a list of Booleans with a Boolean function, fine, you can do that with foldar. You can take a list of any type. And if you have functions of the right types, you can use foldar to combine the list elements. So these types with type variables in, they are much, much more flexible than types without variables. They're called polymorphic types, and they were introduced in ML in the 70s. And they were so incredibly useful because they give you essentially the flexibility of dynamic types. You can use a function like foldar on many different types of data, but you still have the safety of static types. If you make a mistake, the type checker will detect it. And this was such a good idea that every statically typed functional language since ML has borrowed some form of this type system. And more recently, many mainstream languages have also adopted polymorphic types, although often under a different name. In Java, they're called generics. But this is another idea that originated in functional programming that has, I think, taken the world by storm. And this type system is so powerful that many people will say of a Haskell program, once it type checks, it works. Now, of course, this is not strictly speaking true. Of course, you can write Haskell programs with bugs in. Nevertheless, there is some truth to it, and it's surprising how often a Haskell program will work first time. That is, the first time that the type checker accepted it. So the benefits of a powerful type system like this are enormous. So enormous that there are big efforts going on to apply this kind of type system even to languages that don't have them. For example, Facebook have made a huge investment in taking PHP code and translating it into a new language, Hack, their own language, which is basically typed PHP, and converted millions of lines of PHP code so that they can type check it and find all kinds of bugs. It's often said that types are the world's most successful static analysis. I think that's certainly true. But wait, there's more. Dependent types. Dependent types, I don't have time to explain in detail, but what they are types that can depend on values, and they let you capture more information in the types. They let you capture invariants and specifications in types, not just what kind of data you're working with. And that means that the type checker can check that you're preserving your invariants and you're fulfilling your specifications. When you use dependent types, it's really true. Once it type checks, it works. And there are some impressive success stories using dependent types. One of them, in Chrome and Android. Whenever you visit a secure web page in Chrome or on your Android phone, then some cryptographic code runs. And that elliptic curve cryptography code for SSL, nowadays it's generated from functional programs whose types guarantee correct results. And this is impressive work done by Adam Schlipala and his students at MIT. Another example, the most impressive one I know of, CompCert, work of Xavier Leroy at INRIA. This is an optimizing C compiler whose types guarantee that it cannot generate wrong code. Imagine that. Compiler bugs are a thing of the past. And that's intended for safety critical applications like the code that runs in airliners. And it's a huge achievement. So these are success stories where the type checker can guarantee that these programs are bug-free. But it took heroic effort to make this work. Nevertheless, dependent types are a spectrum. So you can start off at the easy end and just check a few invariants, just get a little bit more certainty from the type checking the compiler that your code is right. And you can go all the way to types that guarantee full functional correctness. A lot of people in the functional programming community are interested in taking a walk along the spectrum. And exactly where they'll end up, how much is worth checking in the types, well, that remains to be seen. But this is one of the ways in which functional programming is developing. But very many people are interested in getting stronger and stronger guarantees from the compiler about what their code will do. If you'd like to learn about that, then I would recommend using a programming language called Idris. This is the best language, I think, for actually programming with dependent types. And the language designer, Edwin Brady, has written a very nice book called Type-Driven Development with Idris, which you can find on Amazon, for example. And I recommend that highly. So I want to talk about one more example of an application. And it's these people in the yellow box down at the bottom of the slide. So what's on this slide? It's a list of the top cryptocurrencies by market cap. That is the value of all tokens. And you can see that Bitcoin is the most valuable cryptocurrency, then Ethereum, both well known. And after that, there are a group of coins that vary in total value between about $35 and $70 billion. One of those is Cardano. And the order varies from day to day as cryptocurrencies go up and down. That's cryptocurrency for you. Sometimes they're the third largest. Yesterday, when I captured this picture, they were the sixth largest. But they're up there among the top few cryptocurrencies. What makes them interesting is that they are the world's largest proof-of-stake cryptocurrency. I'm sure you've heard of proof of work. Proof of work is the way Bitcoin works, and that's why Bitcoin is burning energy like there was no tomorrow. Proof of stake is the alternative. It is far, far cheaper. It's energy effective. And if you ask me, proof of stake is the way of the future for cryptocurrencies. And Cardano are the biggest currency who have made it work. But not just that, their entire blockchain is implemented in Haskell. They make heavy use of types. So for example, at the network level, they use types to guarantee that the code follows protocols correctly, to guarantee that there can never be a deadlock. How cool is that? They make heavy use of property-based testing. They have a smart contract language that is about to be released. You write your smart contracts in Haskell. Existing smart contracts are usually written in Solidity, which is a very error-prone language, and you may have heard of the millions of dollars that have been stolen thanks to bugs in smart contracts. Hopefully, smart contracts in Haskell will be a lot more reliable. You still need to test them, of course. How will you test smart contracts in Haskell? With property-based testing tools that are delivered along with your smart contract wallet. It's no accident that this project is using a lot of functional programming techniques. Among other things, they have hired some top functional programming people to work on the project. There are some of them there. So this is a very exciting project. It's one to watch, one to keep an eye on. I've talked about a number of key ideas today, key functional programming ideas. I've talked about immutability, lambdas and higher order functions, domain-specific languages, property-based testing, types and verification. And I've shown you some very high-profile applications that build on functional programming, build on these ideas. These are all ideas, though, that may have originated in functional programming, but they have spread so that many of these techniques and ideas you can use in your favorite programming language, whatever it is, although it may be more effective to use them in a functional programming language. But whether you pick up a functional programming language and learn it or not, functional programming techniques should be a part of your toolkit for the future. That's most of what I want to show you. I just got one more thing. It's Excel. Look, here's a spreadsheet. I've gathered the names of some well-known functional programming people in column B and the country where they live in column A. I got this off a IFIP website. Okay, so I've got these people in my spreadsheet, but maybe I want the names in a different form. Like maybe I want them to look like this instead. Just take the surname, taking Phil Wadler's name, and I just put Wadler brackets GB. So obviously, I could write some code to transform the first two columns into the third, or I could go through and do it manually. That could be a lot of work. Or I could press Control E. And if I press Control E, this is what happens. Wow! Excel did it for me. How did that happen? This is called flash fill. And what happened there was that Excel looked at the first row and it synthesized a little functional program that transforms the first two columns into the third one. And then it ran that program on the rest of the columns, the rest of the rows in the table. Program synthesis. You can synthesize functional programs because they're small and compact, so it's feasible to do that. And program synthesis is something that I think is very, very exciting for the future. I can't wait to see what it will develop into. At the moment, it's in its infancy. You can use it in Excel, but not many other places. But I think it will be very exciting to see what program synthesis can deliver in the next decade or two. And that is what I have for you. Kavi, how do I stop sharing my screen? Oh, I know.
Escape. John, you never disappoint. Thank you very much. It was a beautiful story, very well told. I've forgotten what it was like to have a, technical story told to me so beautifully. And I think you will have amongst us a large number of people who are sold on this idea of functional programming. But I'm sure there are lots of questions. But let me start with one question here. There are many applications that lend themselves to functional programming, and you mentioned a few of them. The only one that was not intuitive that it could be used for was Erlang, for Ericsson to write the switches, right? Could you throw some light on how functional programs might lend themselves to other types of computation like stream processing and stuff like that? I know that is partly what Mary does, and partly what happens in things like Lustre and SCADE and these kind of paradigms. But what has been the functional programming response to those kind of paradigms?
Yes, so stream processing, that's another example where you want to you compute an output that depends on the input. Right? So what you're trying to construct is a pure function here. So functional programming is in principle nicely applicable. But you have to think of, when you have an input stream, you have to think of the collection of all values over time. Think back to lazy evaluation, right?
Yes.
So the output stream is a function of the input stream. And if you want to address that kind of problem with functional programming, then you need to think of it that way. And then you compose functions together, and it's like making a pipeline of functions that each processor stream generate an output stream. So nowadays, when I talked about MapReduce, initially MapReduce was used largely for static data sets. So you'd have your collection all stored in the cluster at the same time, and then you process it and get some results out. But of course, nowadays, you also want to get real-time responses, which means you want to stream data through. And there are streaming languages that compile down to MapReduce jobs, but let you program at the level of streams. I forget, the latest Google thing does that. I forget what it's called now.
Okay,
that
the
makes
reason
sense.
I asked,
You were also wondering about Erlang for telecoms, were you? Were you wondering
Yes.
why it was a good choice, or why Ericsson designed it?
Yes.
So they were originally building telecom products with it, like telephone exchanges. And if you think about what telephone exchanges do, then they have to manage very large numbers of concurrent phone calls. So there is a huge amount of concurrent activity going on. And Erlang was only ever targeting the control plane of these systems. So there was the first big Erlang project was for a switch where every rack contained 2 cards that ran Erlang and 20 that were shipping the data around. And those were in C++, actually, they weren't Adlang. But there's a need to manage an enormous number of concurrent activities. But each concurrent activity here, it would be the thing controlling a call, deciding who to connect, when to disconnect the call, perhaps how much to charge, and so on. So each activity isn't computationally intensive. It's just got to do the right thing at the right time. So they wanted a programming language that could nicely support very large numbers of lightweight processes. And they had previously designed other programming languages that could do that, but weren't functional. And then the team led by Bjarne Dekker at Ericsson CS Lab looked at functional languages and concluded that if they just added a couple of constructs for message passing, they would be ideal candidates for writing this kind of application. So that's where Erlang first came from. And then they built a very, very successful large product using it. And then there was, there was disagreement in the company. So it was actually banned in the company for a while. And this was because arguments about programming languages often become religious, and they're not necessarily resolved by reasoned argument. And so for some reason, Erlang got into somebody's bad books, and so they weren't supposed to be using it until multi-cores came. When multi-core processors arrived in Ericsson Labs, they took a dual-core processor and they ran C++ code on it, and it didn't go any faster at all. And they ran their Erlang system, and it went twice as fast. So once that had happened, it wasn't long before they reversed the ban and started using it again. And that's really been key for Erlang's success, that it performs very well in parallel systems.
Oh, excellent. There'd be a number of questions, I'm sure. We have a colleague, Paritosh Pandya. We have Uday. Would anybody else like to? I wouldn't like to hog John's time here. Would you like to put it out on chat or something?
Sir, can I ask a question?
Yeah, Khalid.
Professor John, I have a question related to the example that you showed on factorial and about the car. So you said that in the Haskell, you create a copy of that same uh, car example, right? So if that particular Volkswagen wants to convert that color of the car to to red. So in that case, and as well in the factorial example, as you said, both the n value is not destroyed, right? So what happens when we try to write longer programs with more variables, and how does the memory management, it is done? Because so many variables still uh, will be present in the heap, right? So how does it work?
So indeed, the way that you write functional programs is always that you never destroy old data, you construct new data that is a copy of it with some changed fields. And so you're allocating new data all of the time. And to make that practical, you really need garbage collection. And so garbage collection originated in Lisp. And it was originally something that was associated with functional languages. Nowadays, it's mainstream. But you have to have garbage collection. Functional programs in a language like Haskell, they allocate memory very, very fast. Like I remember some benchmarks that showed that Haskell programs allocate memory 10 times faster than Java programs. And so that means there is a lot of garbage being generated, because although you allocate memory rapidly, you also very often discard the old value. So data is becoming garbage very rapidly. And that means that you need to have a garbage collector that is very good at recycling short-lived objects quickly. And generational garbage collectors with a fairly small nursery area are very good at that. So that is the way that the Haskell garbage collector works. And again, you have to build your garbage collector now, taking into account the way that you know functional programs are going to operate. But if you do take that into account, then you can get good performance as a result.
I think a corollary to
Okay.
that question would be that typically one associates functional programming with recursion, and recursion implies stacks, which are extremely wasteful of memory. So, does it make sense to kind of allocate that stack and keep on garbage collecting it, or convert it into a more efficient form? So, is there much transformations being done where you convert these things to tail recursion, as you call it, in the compiler itself?
I don't think automated conversion to tail recursion is done in GHC, or it's done much in compilers, but certainly, I mean, you refer to tail recursion, of course. So when a function calls itself as the last thing it does, then that's a tail call, and it's not necessary to keep the previous stack frame. So you can just put one stack frame in the same place as the previous one. And you get the same code from a tail recursive program as you would get from a loop. And of course, programmers know that. So people don't write code that will recurse extremely deeply. Instead, they write tail recursive programs that make efficient use of the stack. And in fact, functional programs like Haskell programs often use rather less stack than conventional programs. Lazy evaluation helps with that as well. Okay. So the stack isn't really a problem.
Okay. I see a question brewing with the Paritosh.
Okay.
Sir.
Hello, John. Thank you for a very interesting talk. Lovely to hear, the recent view on functional programming. My question was more about the quick check property testing. Hi, are you able to hear me?
Yes, I can hear you. Yes.
Yeah. So what is it that makes a quick check fast? I mean, compared to, let's say, an enumerative testing of inputs or randomized testing of inputs? I'm sure there are tricks there.
Okay. Yes. So I think you're asking about the way that QuickCheck generates test cases, and it actually does it by
Yes.
random generation. And an alternative would be to enumerate all possible
see.
test cases.
Okay.
So enumerative testing, usually there are infinitely many possibilities. So you have to enumerate in some order, and that's done by tools like small check and lazy small check in size order. So that you start with small test cases and then you gradually increase the size.
Right.
What we found is that as the size of test grows, so of course the number of possible test cases grows exponentially.
Mm-hmm.
And that means that when you use enumerative testing, you cannot get beyond a certain rather small size. And very often, the bugs that we're looking for don't appear at those very small sizes. I mean, I showed that QuickCheck gives us a minimal example, and that's really important for debugging. But even those minimal examples are often larger than it's feasible to reach with an enumerative approach. So, enumeration can be useful in some cases, but in very, very many cases, it's better to generate random tests and then do what QuickCheck does, which is once we've found a random test that fails, we shrink it. We search for similar but smaller test cases that still fail.
I see.
I can give you an example. Very, very often, we may be generating tests that do a sequence of things.
Right.
So suppose we're looking for a sequence of 5 things that make something go wrong. You could try to search all sequences of length 5, but it's much better to search random sequences of length 30, say. Why? Because very often you've got these 5 critical steps that will cause a failure. It often doesn't matter what else you do in the sequence. So if this isn't always true, of course, but it's often true that if those 5 steps appear anywhere in your sequence of length 30, you'll provoke the bug. So now ask yourself, how many subsequences of length 5 are there in one sequence of length 30? A lot. So we're getting exponential benefit in the amount of work that we're doing. And that's one way to see why it's so extremely effective. As long as you can shrink down to the minimal case afterwards, which we can. Okay, I've got another question here in the chat that I can see.
Yes.
Okay, Kalind Arya, shall I read it out, or do you want to ask the question?
Kalind, you can unmute your video and ask the question, maybe.
Sir, I will just talk with audio, I think.
Sure, do
So,
that.
sir, the question is, as you said, that the memory allocation is faster, like 10 times better than the Java, as you said. So, while creating processes and while processes are, I mean, will this multi-threading and multiprocessing that we do in normal, languages such as Python or others, will functional programs, functional languages will work much better and quicker than those?
Yes. So again, this is a little bit dependent on what you optimize for. So in the Adlang system, for example, then the designers knew that they wanted to be able to run thousands or hundreds of thousands of processes at the same time. And that means that starting a process has to be cheap. And so they started very lightweight processes. And the processes are not isolated from each other. If you think of operating system processes, then you've got memory protection between processes. But in Adlang, there's no danger that another process will write over your data, because processes don't write to data. So the fact that that you have a functional language means you can get away with less protection, less isolation between processes. And when you don't have to provide as much isolation, then you can make starting and stopping processes cheaper. So starting an Erlang process and switching between Erlang processes, it's much cheaper than switching between p-threads, for example. Haskell is the same. Haskell has some very lightweight processes that are used for writing current programs. Now, of course, you can provide lightweight threads in other programming languages too. And I think they're called things like green threads, which are very, very lightweight. But that's the kind of concurrent process that functional languages have had from the start. And that's one of the reasons why Erlang systems early on outperformed C++ systems quite dramatically, because the overhead of having multiple concurrent processes was so much lower in Erlang. I mean, that was what they had spent their time optimizing. And that led to better system performance overall for these kinds of highly concurrent applications.
Okay, okay. Thank you so much, sir. Just one last question.
Okay.
Sir, so can you give an example where such languages are deployed on actual hardware, such as like any kind of a processors or microcontrollers?
Oh, well, I have a colleague who has put Lisp on a microcontroller for a bit of fun. So you can do that. Functional languages that have a bit more memory. I mean, microcontrollers, very often you need static memory allocation. The resources are very, very tight. And if you have a language that fundamentally needs garbage collection, then it's harder to fit that onto that kind of platform. So very tiny microcontrollers are probably not the promising application area for functional languages. Although there are people working on doing that. There are functional languages that are used to generate code that runs in GPUs, for example. There's a language called Futhark, developed at the University of Copenhagen, which is very, very nice and lets you write high-level programs that do array manipulation and then compiles that down to efficient GPU code. So if that's interesting, then you could look up Futhark as the reference.
Okay, thank you, sir.
Sure.
We have space for one more question. I think we've tested John enough because his voice is kind of showing it. Yeah, anybody would like to ask a question? Ameya, I thought you might have had something.
Yeah, I actually, am I audible?
Yeah, could you unmute your video?
Sure, just give me 1 second. I'm not sure if I unmuted it, but yeah. So essentially, no, my questions were mostly again towards the same, towards, are functional programming languages more memory efficient, or are imperative languages more efficient when it comes to memory stack? Because mutability. So Python, the reason why Python tries to mutate the like to make changes in the existing object is to optimize at the memory layer. But when it comes to, I think, something like Haskell, it is creating new objects. So I think that is sort of a the app, like you need to weigh your whether you need a memory intensive program or whether you're okay with having memory, like more RAM allocated to your program. You have to weigh your uh, you have to know that before you go for applying, like using, like picking a language. And same goes for something like Datomic, which you had mentioned, the database. Again, databases are in generally like require more memory so that they respond to queries very quickly. So yeah, I'm still struggling with the fact that Haskell is I would prefer using a more less memory intensive program as compared to something like this.
So remember, what Haskell is doing is where you might update memory in Python, in Haskell you're going to create a copy.
Right.
But when you create many copies of the same data structure, they're only ever going to live in the level 1 cache. So before you run out of cache, there'll be a garbage collection that discards them. So if you look at the memory traffic down the memory hierarchy, it's likely to be very similar. I think if you build the same application in Python and in Haskell, the chances are that the Haskell version is going to be faster and use less memory.
Oh,
But you have to try it out. I mean, the Haskell compiler is very good. It generates very good code.
Okay.
Python is not known for its speed.
True, very true.
I think, John, a very important argument which has not been pushed is the fact that my example that the only programming language in which I got a program to work the first time was a functional programming language. So people seem to give too much respect to machine time rather than human time, because most time after a program is written is spent on maintaining it, extending it, making it work with other stuff, and so on, where imperative programs are no competition whatsoever to the functional paradigm. This whole notion of referential transparency is so important that you can take out a fragment of code and replace it with something else which is proven to actually have the same compute the same function, and your entire edifice should work exactly as you expect it to work. That's one thing I would like to sort of highlight to our friends here about functional programming also. But you brought all the points out very beautifully, John. I must thank you for that, and you've told it as a very interesting story, right? Building it up layer by layer. It's a work of art, I feel. I should go back to this presentation, and it shows the tremendous experience that you have in this space, that you very carefully chose your examples. It reminds me of the lectures of Tony Hoare at Oxford, where after a lecture you felt a sense of, that it's been a good performance.
Well, thank you. I'm
And the
very
person
flattered.
hasn't lost you. Right. So thank you very much. You've presented this very beautifully. And I'm sure that our friends here are going to perhaps go back to this. And also, it would have prompted them to think again about the things that they regard as given. And I think this also represents the future of programming, because functional programming has got so many important properties which are beginning to come to light as we go along. And I think you played a very important role in that. Must thank you for this, and thank you for a very engaging talk. So, John, a big hand from all of us.
Thank you
For
very
a
much.
wonderful talk. And we'd like everybody to unmute their video. We'd like to do a photo up here, at least of the guys in the room with us here. It's being streamed live on YouTube and Facebook, but at least the ones in the room here should unmute their videos, and we'll just do a photo up. So Paritosh Pandya here, incidentally, is a colleague who's worked at TIFR and formal methods, model-based design. He's been a close associate of Gerard Berry, and he's also worked with Tony in Oxford.
Ah, nice.
Paritosh, we can't hear you.
But it is very, very, very. We had people like Richard Bird, who showed us the greats of functional programming, and it's very inspiring. I had one thing that I wanted to ask you. I mean, you place such a beautiful emphasis on typing, which we think is one of the strong points of more literate programming. And yet, dynamically typed languages, Python seem to catch on so much. So psychologically, do you see why this is the case? I mean, is it such a burden typing your programs?
So I think, especially for beginners,
Yeah.
then typing can be a little difficult
I see.
because if you take a dynamically typed program and it adds 1 to a Boolean, it's going to tell you exactly what went wrong. This is what you did. You added 1 to a Boolean, and you can see, oh yes, of course I can't do that. Whereas if you try and do the same thing in a Haskell program, the type checker is going to complain about something, and exactly what. It may vary. So you have to understand both the dynamic semantics and the static semantics, and they are different. I think that is a little bit of an obstacle at the beginning of a programmer's education, and that could be why people who just pick it up without a thorough education maybe like to pick up a dynamically typed programming language. But in the long run, I think when you've done a lot of programming in typed languages, you really appreciate having your bugs found immediately by the type checker.
Absolutely. Thank you.
Thank you. I would like Suprabha to take a photograph of whoever can be seen. I think people are very shy here, it seems. But I certainly want this picture with John, Paritosh, and a few of us here. Very good. Who'll take the picture? Is it Deepa?